Hello everyone, welcome to Data 609 Module 7, and we are also in the Chapter 7 of the textbook. This section we're going to discuss support vector machine and regression. So if you ever heard of support vector machine, it's one of the classification algorithm. And here we'll take a deeper look at the underlying formulation for support vector machine. So first of all, you should be aware that support vector machine is a classification algorithm. So what is classification? What is clustering? Classification has labels on the data, so it's also called supervised learning, one type of supervised learning. So in this example here, it's a binary classification, so that you want to classify the data into two categories. One of them is denoted by the red circles, and the other one are denoted by the blue squares. So in order to classify those two groups, the diamonds and circles, what we can do is we construct a hyperplane with a normal direction of W, so that W times X dot product X plus B equal to 0, or W transpose X plus B equal to 0, so that these samples can be divided into two classes on two different sides. So first of all, you have to have this existence of hyperplane, otherwise the approach doesn't work. So what we're trying to do is we can construct such a hyperplane. We should construct two hyperplanes that shows as the green dotted lines, so that they are so as far away as possible, and no samples should be between these two planes. So instead of constructing this one line of the pink or purple line in W dot X plus B equal to 0, you could construct those two green lines, that's Wx plus B equal to positive, and the other one equal to negative, so that you can differentiate those two classes of data points. And then it can be also compactly written as this form: W times X plus B equal to positive or negative 1. So the normal perpendicular distance between these two dashed green line hyperplane is related to the W norm, and that distance is 2 over W norm. So from the optimization point of view, the maximization of the margins can be written as trying to minimize a half of this W norm squared. So instead of trying to maximize this distance, what we're trying to minimize is basically some sort of form of this squared inverse of that, right? So we're trying to minimize this. Again, what does that mean? We're trying to find a maximize the distance, so that with those two hyperplanes, we're able to separate those two different classes. Now, instead of maximize this distance, we're trying to minimize the inverse of this distance, function of the inverse of this distance. Now, once we are able to minimize this, we can classify all samples into that if each one of this form larger than or equal to positive 1 into one class, the other one into the other class. So essentially one class belongs to larger than 1, the other class belongs to this direction, less than or equal to negative 1. because we label the data of the y to be +1 or -1, those two equations can be rewritten as with the y in the equation, so that y times whatever we have previously larger than or equal to 1. It's the same way for the one that's being on the negative side. So it is not, now we actually have this relationship. We are able to have this relationship to classify the two types of data. However, it's not always possible to construct such a separating hyperplane. There's a chance that you have to introduce some sort of slack variable. Slack variable helps you to, instead of larger than or equal to 1, strictly you use some sort of slack variable so that you can use 1 minus this, so that you have some sort of error. And then now you would be able to have this relationship. Once we introduce this non-negative slack variable of eta, now the optimization problem is no longer trying to minimize this first component only, but also trying to minimize the first component as well as the non-negative slackness that we introduced there. Sum all of the i's together from 1 to n, and then subject to this equation being valid. Now you see that we introduce this lambda as well. Lambda is some penalty parameter with the hope that this lambda can drive all of this eta close to 0 if not. And then this sum of eta is essentially a measure of the upper bound of the number of misclassification on the training data. So we allow some sort of misclassification just because we're not able to find a 100% separable hyperplane. Now we allow for that, but we want to penalize that. That's why we have a lambda in the objective function, and lambda itself is larger than 0, so that we can drive this summation to be as minimal as possible. Now, once you have this relationship, we know that we have a quadratic function in the objective, and then we have a constraint, and then we can leverage Lagrangian multipliers to solve this problem. And then with the Lagrange L, this is the formulation, and then from this, you can write the KKT conditions that we discussed earlier in the semester in chapter 2 and 3. Now you can use partial order derivative, try to solve this problem. So that's support vector machines. That's the formulation. What you need to know is it's a quadratic problem with the objective function being minimize the inverse of the distance plus a penalty term, and that penalty term is a measure of the upper bound of the number of misclassifications on the training data. So that's support vector machines. And then we just discussed the linear support vector machines. How about nonlinear support vector machines? So in other words, what's happening is there's a chance that the data cannot be separated by a hyperplane. So we have to use something called kernel tricks to transform the original data into one space to another easier space. So if you think about what we have on the left-hand side of the chart, it's just impossible that you find a linear hyperplane to separate those two sets of data, sets of observations. Then you can use kernel tricks to transform what's shown on the right-hand side. Now it's separable. You are able to find the hyperplane. Okay, so the kernel trick is to find just basically transformation. So what it does is, for each observation, you do the calculation based on certain transformation so that you can have a new observation. Just like what we discussed in the principal analysis, principal component analysis, we transforming the original data. Of course, it's in a different way, right? Here we use, most widely used method is called Gaussian radial basis function, so that you are able to translate original observation data to a new feature space, a new observation. And then the gamma that's used in the IBF is a hyperparameter. There are many other ways of this kernel trick. You should be aware of that. And also you should be aware, in which case, which kernel that I may want to try. Of course, it has to be the proper one, and that actually works for your data. So for now, you just be aware that there's something existed. In case you're not able to linearly separate them to find the hyperplane, you can use kernel trick to transform your original data. That's nonlinear support vector machines. Moving on, we want to discuss support vector regression. So support vector machines for classification works really well for discrete labels. As we just discussed earlier, right? We have two sets of labels. One of them is +1, the other one is -1. But in case of a continuous dependent variable, instead of binary or categorical, if it's continuous for the y variable, you want to use support vector regression. So support vector regression is something that's beyond support vector machines, but it's the same family of problem. So for given tolerance, eta, this error term, this eta epsilon, for a given tolerance of epsilon, the epsilon intensive support vector machine is to find a y equal to fx, which is, this fx is w dot product x plus b, such that all the data points are within a strip bounded by two blue hyperplanes. So we're trying to, similarly to support vector machine, we're trying to minimize this half of w norm squared subject to y minus w dot xi minus b less than or equal to epsilon. That epsilon is the tolerance that we initially defined. And then again, this is apparently optimization problem, and you're able to use optimization techniques to solve the problem. So what if, same thing as what we discussed in support vector machines, you have a relaxation of the eta term just because you're not able to find a totally linear separable hyperplane. In here, what if you are not able to bound all the observations within these two lines? Then what you need to do, you somewhat relax on both ends with different parameters, xi and xi star for different side, so that you're able to relax that constraints. Now, once you have that new slack variable, you want to use a new parameter, lambda times xi plus xi star, to be in your objective function. Again, you want to drive this summation as small as possible. The lambda is larger than 0. You want to drive this as small as possible so that you are not going to have a gigantic two lines that's very far away, right? In other words, we want to have that two hyperplane as close as possible. Meanwhile, we want to contain all the observations within those two lines as much as possible. That's the idea here. So with those being the objective function, minimize the inverse of the distance plus lambda times this relaxed term slack variables. Now we use the same constraints and try to solve this optimization problem. Again, here the penalty parameter lambda larger than 0 controls the trade-off between the flatness of the regression model, fx, and the deviation errors. So in the context of machine learning, we can use epsilon intensive loss function, Kc absolute value eta for support vector regression, and then Kc eta would be when the Kc epsilon would be when the Kc less than absolute value of Kc less than epsilon is 0. Otherwise, it's Kc absolute value minus epsilon. So what you saw on the right-hand side, this is really the curve, basically saying that anything within this error term is 0. Beyond that, you use Kc absolute value minus epsilon to be the your Kc epsilon. And this problem can be solved in using the KKT conditions and solve it using suitable optimization techniques, because both of them are implemented in many of the machine learning packages. So here we're now going to discuss the solution algorithm in further detail. At least you are aware, you know, what's the difference between support vector machines and support vector regression. One is for discrete categorical variable, the other one is for regression continuous variables. That's number one. Number two, what's the formulation of support vector machines? As I discussed earlier, we're trying to find linear separable hyperplane that has a quadratic term in the objective function, which is the inverse of the distance plus some sort of error terms that we want to minimize. So that's the key points that we want to discuss, and also you want to be aware of the loss function, epsilon intensive loss function that how that might be defined. So that's something that would definitely be useful in the sense that you have a better understanding of the methodology itself. Okay, that's in terms of support vector machines and support vector regression. And here are some references. R has a package called SVM, and MATLAB has fit C SVM and fit RSVM. And Python also have SVM with our algorithm variants that we can explore. And then SVM and SVR are also implemented in C++, Java, and other machine learning languages, packages. Okay, for now we'll stop here today on the support vector machines and support vector regression. Thank you.